Hey guys, what's going on? So today we're going to be looking at SU2 spin-1 tensors. This is coming from the last video that we talked about when we were talking about the spin-1 objects that were necessary to attain invariance in our SU2 Lagrangian. Okay, so we're getting a little esoteric here. What I'm going to do in this video is we're going to go over those tensors that we need to go over in order to understand how all this works. But I'm also going to, there's going to be exclusive content attached to this video as well, just like there's been more exclusive content being posted on these videos on my Patreon. So feel free to go onto my Patreon to get that exclusive content. If not, you can still get all the necessary information from these videos. Now let's get right into the topic. Make sure to hit that like and subscribe button also. Okay, so we're talking about the SU2 spin-1 tensors. So we have three new spin-1 fields that transformed in this way. This is the punchline that we came to in the last video. So our main goal here again is to get the F mu nu analogs for the spin-1 field to build a Lagrangian that describes how these new spin-1 objects behave. There are a few things that we want to take note of, okay? So it's going to be conventional to write these vectors in this way. So we don't always have to write out the Pauli matrices, okay? Our field strength tensor is going to be written in this way because the tensor, again, is a two-component object. It has the two indices. We also want to take note that the trace of matrices is behaves in this way, right? So if A, B, C, and D are matrices, the trace of their multiplication when we perturb them in these ways are all going to be the same, okay? And what I don't have here is an R, like that. Okay. We are also going to demand that the tensor can be written in this way also. Okay, so the transformed tensor can be written in this way so that the trace remains invariant. What we mean by that, again, is that if we take the trace of two of them, of two of our tensors, then when we prescribe this here, these two guys are going to be equal to 1, and then we get this relationship here where we can bring our inverse transformation over to the side. Those two guys will end up being 1 also. These two guys are 1. And we get the trace of our matrices again, or of our tensors again. Okay. Earlier we said also that we can transform our field objects. Right? These are our spinner-like objects, spin 1/2 objects again. Therefore, the d mu nu, or d mu, must transform in this way. So the derivative also transforms in a specific way, and that's going to be like this. So that derivative is transforming similarly to the tensor, which is interesting. And so because of this relationship right here, what we can find out here is that when we apply this, right? So there should be a prime here. So this is equal to this. We just transfer that prime to both objects. We transform both objects in our SU2 case. Okay, these two guys are going to be 1, and we get this. Well, this right here was the relationship that we were looking for, because this is the relationship that says this is the derivative that enables us to pull that U1 transformation outside of it, so that the Lagrangian can be invariant. You can just go back to the previous video to see that this is the type of transformation that we need in order to have the Lagrangian be invariant. Okay. All right. Finally, we want to say this. Okay, so we want to say that the tensor itself can be defined in terms of the derivative. And in terms of the derivative, it's going to be defined as a commutation relationship, okay, with some constants outside of it. And we say this because when we do this, right, so we flesh out the commutation relationship, and then we multiply both sides by our constants, and multiply both sides essentially by g and divide both sides by I, right? So we get this relationship here. And what we can do now is we can transform each d here. As we've seen, this is how they transform right here. Okay, so we just do that here. Okay, things start looking out as 1, canceling out as 1 here. So we get this, and then we can take our mu's, or not our mu's, right? Sorry, our transformations, our SU2 transformations outside, and we can also take the inverses outside here, and we remain with this. And what we said was that our tensor, again, transformed in this way. We just now have some constants. The constants are going to be important for later, okay? We don't have to totally worry about them right now. So taken together, we have that this, we said this is going to be our tensor, our 2-index object. We say also that the trace remains invariant. We also say that the tensor transforms in this way, and we say that the derivative transforms in this way. Okay? And then we say that the tensor can be written in terms of our derivatives. Okay? So these are the 6 things we want to keep in mind when we start to develop the tensor that we're looking for. So we now are ready to see what these guys are going to be like. They're going to be the analogs again for the U1. In the U1 case, it was F mu nu. In the SU2 case, it's going to be W mu nu. Okay, here's the W mu nu. This is the punchline that we're going to get to. Okay, again, I want to give you the punchline because those of you who might not be interested in going to exclusive content where the longer derivatives take place, that you at least get this is the punchline that we're going to get to. Okay, and so with that being said, make sure to hit that like and subscribe button, and I will see you guys in the next video. For those of you who are into wanting to see how this thing gets derived, continue with me on my Patreon, and I will see you guys in the next video.